Okay, Precalc class, here we go. We're going to go over every problem from the Parametric Equations packet that we didn't do together in class last week. I think I said I was going to make this video like a long time ago, but you know, things got kind of in the way. So alright, let's throw a nice title up here, Parametric Equations, and yeah, let's begin. Let's begin with number 12, which is actually quite hard, I think. This one we did not go over in class. This was the one that was due on the first day. So x equals 1 over root t plus 1, y equals t, t plus 1. Okay, and you know, one of the excuses for studying parametric equations is just from a sort of math teacher perspective, it's just an extremely good way for students to just practice their huge range of knowledge, as we're getting sort of toward the end of pre-calculus here. So at this point you should just know every function, you should be able to graph every function by hand, you should know every function transformation, you should be able to do sort of sign charts and everything, and all of this will be very helpful in calculus. So here's a good example of a problem which just combines so many different things together. So let's begin. What's the first step? The first step is to note restrictions. And okay, already this is maybe kind of hard. I can only take the square root of positive numbers and 0. So if t is 0, that's kind of okay. Or if t is negative a half, that's okay. Even if t is negative 1, no, actually, once t is negative 1, we already have a problem, because I can take the square root of 0, but a 1 over 0 can't be. So, okay, so a casual sort of analysis here concludes that t has to be greater than negative 1. Okay, what can I say about x? Well, the denominator is guaranteed to be positive because the square root function also always outputs a positive number. So if the square root of anything is positive, then 1 over that thing will also be positive, and so x has to be positive. Fact. And I might even be able to say something stronger, but I don't think so. Okay, what about y? Man, this is getting pretty hard already. What might you do if you were going to perform some sort of analysis on y? Well, we see t can't be negative 1. We kind of knew that already. Maybe I want to say something like y can't be 1. Why can't y be 1? Well, because the only way for y as a fraction, the only way for y to be 1 is if the numerator and denominator were the same, but they can't ever quite be the same because the denominator is always bigger. Now, the thing is that I can't assume that t is positive, because most of the time t will be positive, but t has to be greater than negative 1, so actually there will be some negative t values which are legit. And so this already kind of becomes sort of hard. So alright, to me, this is a good candidate for making a sort of side graph. So, even that is kind of tricky, right? Because what do I know about, okay, so what do I know about root t plus 1? Well, root t plus 1 is going to look like a square root function, except moved 1 to the left. In other words, it's going to look kind of like that, is a graph of root t plus 1. So if that's a graph of root t plus 1, then what can I say about 1 over root t plus 1? Well, it's going to be the reciprocal of that. Okay, and we know how to graph reciprocals. You know, when you plug in, so this was 1, and now as this gets bigger, sort of this will get smaller, and this will get bigger. So we have actually like a vertical asymptote at x equals negative 1, and I have this blue curve. And what am I actually doing? I should remind you, I am graphing, for help, sort of only, I am graphing x versus t. So this is the t-axis, the horizontal axis, the independent variable, x depends on t. So for different values of t, this is a picture of what the x-coordinate is doing. But even making that graph was kind of a two-step process. Okay, what about y versus t? That's also maybe a little bit kind of hard, right? What should I make of t over t plus 1? Well, to be honest, that's a rational function. And so we should treat it like any other rational function. For example, one thing we might do with this is make a sign chart. And the sign chart for t over t plus 1, well, it's going to change signs at -1. It's also going to change sign at 0. And therefore, if all I was asked to do was graph t over t plus 1, what would I say? I would say that it goes positive, negative, positive. That's just right. But there's even something else that I need to do, which is do polynomial long division. So, okay, most people wouldn't actually do polynomial long division in this moment, but okay, you can. T plus 1 goes into t one time, and that gives you t plus 1. You subtract, you get -1, and so in fact, t over t plus 1 is just 1 minus 1 over t plus 1. The fast way to do this is to just add in a phantom plus 1 minus 1 up top here, and then if you do it that way, this is what a lot of people kind of do who are experienced. If you throw in a little plus 1 minus 1, then you can just split that fraction up into 1 minus 1 over t plus 1. Okay, but of course you can just do the polynomial long division. It's what I did. So what am I even doing here? What I'm doing is I have sort of two representations, as we often did in the rational functions unit of this function. So let's graph it now. What does it look like? It has a vertical asymptote at -1, so cha-cha-cha-cha-cha-cha, and a, what else? It's going to be basically like, it's pretty much going to be like a 1 over x graph, but upside down. Also going to get moved up 1, and upside down. So therefore, let's see, oh, and there's a root at 0, so I claim that, there's a root at 0, and vertical asymptote at -1, and, well, it looks just kind of like this. And I guess, if I wanted to, I could even sort of consult my sign chart to convince me that I've done everything correct. Alright, so what's this? This is just the graph of y versus t. So every single thing I've done so far now is sort of like optional, just to help me understand what's going on. But I think that help is pretty important. And notice now that looking back, this is a little bit misrepresentative, because in the graph of x versus t, we see that only t values greater than -1 are permissible. And therefore, this part of the graph here, I'm going to kind of, I guess I'll just erase it, because it's really not there, because t values less than -1 really aren't allowed. Okay, so I have a graph of x versus t, and I have a graph of y versus t. Did I absolutely need to do this? No, not absolutely, but it's actually quite hard to see. So, for example, I now know, after making this graph, that it's not only true that y is not equal to 1, a more full version of the story is that in fact y is always less than 1. But I think without doing that graph, I don't think I could have seen, I don't think I was smart enough to just look at t over t plus 1 and to know for sure that y had to be less than 1. For positive values of t, I guess you could do it if you were quite smart, right? For positive values of t, the numerator is always smaller than the denominator, so indeed y would be less than 1. And for negative values of t, the numerator is just negative and the denominator is positive, and so it's just negative, and so therefore is less than 1. So you could do this without graphing, but it certainly helps to graph. Okay, let's kind of push the pace here a little bit. What am I supposed to even be doing next? Well, I'm supposed to be looking at end behavior, so I'm supposed to be examining what happens as t approaches infinity. And, okay, I can do this from just looking at my functions and see that if I take the square root of something like 1,000,000, it's still pretty big, like 1,000, and so this denominator is just going to keep growing and growing, so 1 over huge is 0 plus. And what about y? Well, once again, using just kind of common sense, if you plug in 1,000,000, that's pretty much 1,000,000 over 1,000,000, so this is going to 1. But is it going to a little bit more than 1 or a little bit less than 1? Well, a little bit less, right? Because the denominator is always 1, the numerator is always 1 less than the denominator. Okay, I'm not going to look at negative end behavior because in fact t can't be less than -1, but I should observe in both of my equations things kind of get crazy near -1. So I should investigate what happens as t approaches -1 from the right. So what happens when t is a little bit more than -1, like -0.9. Okay, so I have only the equations way of doing this is to say, okay, t is like -0.9, which makes inside that square root a tiny positive number. If you take the square root of a tiny positive number, it's still a tiny positive number, and 1 over that tiny positive number is infinity. Now, if you give me a number which is a tiny bit less than -1, okay, this is quite tricky now, right? Like -0.9. Well, if you add -0.9 and 1, then you get a tiny positive. Okay, so that's a tiny positive in the denominator, which you would think would make the thing huge. In fact, it will make it huge. But recall that if the top is -0.9, then what we have is a normal negative number divided by a tiny, tiny positive number. And if you give me approximately -1 over a tiny, tiny positive number, that's going to make the magnitude of the number infinite. And so what we're going to actually get here is -infinity. All right, so I can do that in my head, but by being very sort of careful and experienced. But notice that it's probably just easier to take the extra time to make these graphs and consult and see that indeed, if I'm a tiny bit more than -1, x is going to infinity, and if I'm a tiny bit more than -1, y is going to -infinity. Okay, so the value of these graphs, I guess, is in sort of being able to answer the restrictions and the end behavior step properly. Because once you do this, then things are just kind of easy now, I think. So I'll erase all that in a second, but first let's finish our other sort of preparatory things. I need to eliminate the parameter. So okay, let's do it. Let's take this x equals 1 over root t plus 1. Let's you know, kind of reciprocate both sides, or however you want to say it. So 1 over x is root t plus 1. I'm solving for t now. So square both sides. If I square both sides, I get this is 1 over x squared is t plus 1. Well then, so therefore what's t? T is 1 over x squared minus 1. And now, what's y? Well, y is t over t plus 1. So, okay, there are lots of ways to do this, but this is one way, is stick that there and that there. I mean, almost no matter what math you do, it's eventually going to work out. But what do we get? We end up with y equals t, so 1 over x squared minus 1, over t plus 1, which is 1 over x squared. And remember, the whole goal of eliminating the parameter is to rewrite it into some form that I recognize. So I personally don't recognize this. So let me just throw in a multiply by x squared over x squared, and hopefully that will clear things up. What do I get? I get y equals 1 minus x squared. That's it, just 1 minus x squared. Yeah. And so after all that work, it turns out that the relationship between x and y is fundamentally parabolic. Okay, now we will, I see that I'm not going to finish this video in time. So now we will do the graph. So what is going on? Well, x has to be positive, so only the right-hand side of this graph is happening. And y has to be less than 1, which suggests that maybe, you know, this is got a kind of a hole type situation. But otherwise, it's just the parabola y equals 1 minus x squared. And I kind of know what, you know, that parabola looks like. It's gonna, you know, it's gonna look like this. And I'll have this point here, 1, 0. And let's see, if I plug in 2, I get like -3. So maybe down here I have this point 2, -3. Sorry. And there it is. Okay, let's try to make some sense of this with, excuse me, with annotations and such. Right. Well, here we go. What's the first t value that I'm allowed to plug in? That's a tiny bit more than -1. And where am I at time a tiny bit more than -1? Infinity, comma, -infinity. In other words, I am way down here at t equals -1 plus. And I must be moving sort of up this parabola. Let's see, what's a nice number that I can plug in? what if I plug in, let me try to be cool a little bit here. What if I plug in, what will give me 4? Maybe if that was 1/2? No, 1. Oh man. What that would give me 2 if that was 1/2, square root of 1/2, 1/4. So if t is -3/4, yeah. I think if I did that correctly, if t is -3/4, then -3/4 and 1 is +1/4. What's the square root of a fourth? 1/2. What's 1/1/2? 2. And if I plug -3/4 into y, I get -3/4 on the top, and again -3/4 and 1 is +1/4. So -3/4 divided by 1/4 is just -3. So indeed I am at the point 2, -3 at time -3/4. Which means it takes me 1/4 of a second to get from the infinity all the way down to the bottom of this parabola up to the point 2, -3. And then, alright, what's another sort of easy number to plug in? Well, just how about 0? If you plug in 0 for t, then you just get, sorry, panicked for a second. Yeah, if you plug in 0 for t, you get square root of 1 is just 1, so you just get 1, 0. So this point 1, 0 is t equals 0. In other words, it literally takes 1 second to do almost the entire parabola, and by the time we get to time t equals 0, I'm at the point 1, 0. And now what happens is I slowly, it takes me now an infinite amount of time. As time t approaches infinity, what happens? I approach this point, which is a little bit more than 0, a little bit less than 1. And so t equals infinity. So that's sort of the full story. Starting down here at time -1, a tiny bit more than time -1, I shoot up this parabola, covering an infinite amount of this parabola in 1 second, and then taking an infinite amount of time to do this other little jump of the parabola. All right, I thought that was very hard. That problem. Let's try to do a couple more before stop this video and go teach class. Alright, so 13, here we go. What's 13? Okay, x equals 4 times the cube root of cosine. This is also another crazy problem that when you saw this, you're probably thinking, dude, Mr. Rose, I don't know how to do this. Come on. 4 times the cube root of sine. Okay. Whew. Well, there's a lot of things you can do with this problem, even if you have no idea what's going on. For example, well, what do I know about the cube root function? Well, the cube root function kind of goes, you know, like this, right? It's cube root, something like that. Okay, yeah, that's pretty accurate. It's just the reciprocal, not the reciprocal, the inverse of the cube function. So it's going to have this kind of vertical asymptote here. All right, great. Sort of so what? And you know, you have this point here, 1, 1, and this other point here, kind of -1, -1. So you can take the cube root of anything, and it's just a fact that if you take the cube root of a number between 0 and 1, it gets bigger, right? So what is the cube root of 1/8? Well, what is the cube root of 1/8? It's the number which, when multiplied by itself 3 times, gives you 1/8. Well, that's 1/2. So, okay, so sort of maybe picture not sort of perfect, but there it is, right? If you take the cube root of 1/8, you're going to get 1/2. So, all right, fact, the cube root of a number between 0 and 1 gets bigger. And the cube root of a number that's bigger than 1 gets smaller, right? So maybe I'll just write this out. The cube root of 1/8 is 1/2, but of course the cube root of 8 is 2. Okay, these are just sort of basic facts that you learn in, you know, the first month of Precalc C or something. Great. Well, what can I say about cosine? One fact about cosine is that it's always between -1 and 1. That's just a fact. And as we can see from our picture / common sense, if you take a cube root of something between -1 and 1, it's also between -1 and 1. So I can say that the cube root of cosine is also between -1 and 1. And if that's true, well then 4 times the cube root of cosine must be between -4 and 4. And okay, without just sort of repeating this whole logic again, okay, so what does this tell me? It tells me that my x-coordinate is indeed between -4 and 4. My y-coordinate is also true, right? It's also true, I just said I wasn't going to do it, but I guess I am, that sine is always between -1 and 1. That's just the range of sine. And so cube root of sine will also be between -1 and 1. And so 4 cube root sine will be between -4 and 4. And thus we've sort of established something kind of important here, which is that this entire function stays kind of bounded by, and here I'll just sort of draw it right now, that this entire function is going to stay bounded by by a kind of a box of size, a square of sort of 8 on a side, right? So I'll put this little kind of green thing here. Cha 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 cha. Okay, great. Great. What else? You could just plot a lot of points and you would get somewhere. For example, plug in 0. What's the cosine of 0? It's 1. So cube root of 1 is 1, and so you get 4. What's the sine of 0? 0. So you get 4 comma 0. So already I kind of, this shape is sort of coming to get me. I know that at t equals 0 I'm going to be here at the point 4 comma 0, plug in pi over 2. If you plug in pi over 2, cosine pi over 2 is 0. Sine of pi over 2 is 1. Cube root of 0 is 0, cube root of 1 is 1, and so you get 0 comma 4. So I'm here at 0 comma 4 at t equals pi over 2, and here at t equals pi, and here at 0 comma -4 at t equals 3 pi over 2. You can just check that this is true. It just, just like is true. This point is -4, 0. Okay, and so you're tempted to say that this is some kind of a circle of some kind. So alright, this is some kind of vaguely circular thing, and of course, the period of sine and cosine are each 2 pi, so whatever this shape does, it's going to just kind of keep repeating every 2 pi. So we have some sort of shape which is vaguely circular in some kind of a way, is contained within this square, and which repeats every 2 pi. And so the only thing sort of left to determine is like, what's the general shape of this graph? Okay, there's no end behavior to talk about. There are no restrictions on theta, because you can take the sine and cosine of anything, and you can take the cube root of anything. The domain of the cube root function is all real numbers. Okay, what's left to figure out? What's the shape? What's it sort of doing kind of in between? Now, you could plot some points and you could get some reasonable guess about this, but I would like to do something else. I would like to say, okay, first of all, this 4 is kind of a distraction. So let's just solve the separate problem of what's up with x equals cube root cosine theta, y equals cube root sine theta. And if I can determine what this pair of parametric equations looks like, well then my shape will just be that, but dilated by factor 4. Okay, so what now? You can pursue eliminating the parameter. Good luck. But this is a new shape that we've never seen before. And eliminating the parameter is really only helpful when the ultimate answer is something that you recognize. In this case, you're not going to recognize what it is. So I'm not even going to do it. Instead, I'm just going to try to learn right now on the spot, like what is there to say about y equals cube root sine theta? In other words, I'm going to try to graph cube root sine theta. And I'm going to try to learn something about it. Alright, well, what does cube root sine theta look like? Well, I don't know, let's see. So this is now sort of theta and y. Okay, well, first of all, if I plug in, let's use purple for this. If I plug in 0, what happens? So let's kind of do a little bit of this. So that's 2 pi. Yeah, theta axis. Okay, so if I plug in, what I say, if I plug in 0, sine of 0 is 0, and cube root of 0 is 0. If I plug in pi over 2, then, well, then I get just 1, right? Because the cube root of 1 is 1. When I plug in 0, I get 0. When I plug in 3 pi over 2, sine of 3 pi over 2 is negative 1. Cube root of negative 1 is negative 1. So actually I'm starting to sort of observe some kind of phenomenon, which is, I don't know what, I'll write this over here just to clarify that I'm attempting to graph in purple cube root sine theta. Well, maybe what I should now do is compare with just regular sine theta. So what does just regular sine theta look like? Well, it has all these same values, right? And this is kind of not surprising because, so this is my graph of sine. Just a regular little sine graph in red. So what is the relationship between the cube root of sine and sine? And the answer is, it should be actually sort of pretty similar in the big picture. In the big picture is that it's also periodic, it's also bounded between negative 1 and 1, and it agrees with the sine function on all the sort of key points. But then you have to sort of ask yourself, okay, well what about in general, what is going to be the relationship between sine theta and cube root sine theta? And now we go back to the conversation from 5 minutes ago. What happens if you take the cube root of a number which is less than 1? Answer, that number gets bigger. The cube root of a number less than 1 is bigger than the number is. And therefore, if I was to try to make an accurate graph of cube root sine theta, I would say that in general, all the y values are going to be larger. Because for any real number, the sine of it is always going to be less than 1. But the cube root of the sine of it is going to make the number even bigger, but still less than 1. And so what we're kind of now expecting is for a shape which is just kind of like sine, but sort of fatter or something like that. And in fact, the sort of deepest explanation says that, hey, let's not forget that when theta is approximately 0, sine theta is approximately theta, which is to say that the sine function kind of looks like the line y equals x near the origin. Therefore, when theta is really tiny, what should I expect about to say about the cube root sine theta? Well, cube root sine theta is therefore going to look a lot like cube root theta. In other words, I mean, we're pretty much doing calculus now. In other words, we should expect our cube root sine theta function to locally, near the origin, look like the cube root function does. And in fact, that's exactly kind of what you see. That there's this vertical asymptote here. Well, it's not really a vertical asymptote. It's a vertical tangent line. But basically, that if you graph this curve, you will see that near 0 it looks a lot like cube root x looks, and by symmetry it's going to also be locally cube root near pi and 2 pi and all those other numbers. Okay, so I've now done sort of this deep exploration of this function I never heard of, and here's my conclusion. It's fatter than sine is. Alright, well if it's fatter than sine and cosine, and we already know that sine and cosine make a circle, right? That's another bit of sort of background information, right? That we talked about in last class, or 2 classes ago. X equals cosine, y equals sine is the parametrization of a circle of radius 1. So what should I expect about this pair of parametric equations? Well, it's going to be a fat circle. It's going to be a circle whose x and y coordinates at every single point are bigger than the corresponding x and y coordinates in the pair of parametric equations which parameterize the circle. Okay, long build-up. Final answer is, what is this shape? It's a fat circle. And so that's what you draw. A kind of fat circle. I think this was maybe not fat enough, right? Sort of fat circle. And Yeah, that's the sort of the almost official name of this thing. Could I get some sort of support for this? Okay, I don't know. But maybe you want to know what's going on at, say, pi over 4. So if you plug in pi over 4, what do you get? Do I even want to do this? I don't know. Sine and cosine of pi over 4 are the same thing. They're just sort of root 2 over 2, or really it's like 1 over root 2. So, so that's like, okay, so I want to basically take the cube root of 1 over root 2. So that's really like 2 to the negative 1/6 or something. So that's like the 6th root of 2. 1 over it. No, it's, yeah, 1 over the 6th root of 2. Jeez. But then times 4. I don't know, that doesn't lead me anywhere. I changed my mind. I don't want to sort of plot any points at all. I thought I could, I thought that there was something cool I could do here, but maybe there isn't. Is it not true that it's like 2 root 2 or something? No, it's not. Okay, anyway, there it is. I'm happy with that. If you are, okay, good. Let's try to do one more problem. Let's try to do, so that actually, that concludes maybe that's a good place to stop. That concludes the problems that were assigned for the first homework assignment that we didn't also go over in class. And then I guess later this afternoon I'll do the rest of the problems from the packet and put this all together in one big video. Okay, bye! Okay, we continue with this Parametric Equations packet. And we're in the home stretch. Let's go over some other problems from pages 5 and 6, which were due last week. I think we only went over problem 16 in class, so let's just do the rest. So here we go. 15, right here we have x equals absolute value t minus 1, y equals t plus 2. Okay, I think this one is pretty straightforward. What is there to say about this? Let's just go through everything that there is to talk about. Of course, t can be anything. What can I say about x? Well, because x is an absolute value function, then I know that x has to be greater than or equal to 0. What can I say about y? I think nothing. Let's also look at the end behavior. What happens as t goes to infinity? What happens as t goes to negative infinity? Well, yeah, here it is. Let's do it. As t goes to infinity, well, both x and y are going to infinity. And as t goes to negative infinity, x is still going to go to positive infinity because we're taking the absolute value of it. Y is going to go to negative infinity. All right, now I have to eliminate the parameter. Okay, I hope you agree that there's only really one good way to do this, and that is to leave your y equals bias behind and to express this as an x equals equation. And so what I mean by that is set y equal to t plus 2, solve for t is y minus 2, and stick that in here. So what we get is x equals absolute value, y minus 2 minus 1. In other words, x is absolute value y minus 3. Okay, this is just great, and well, maybe I can just squeeze this in sort of right here even, because I think maybe this is not that hard. What is x equals absolute value y minus 3? Well, I suppose this assumes that you have some experience, or at least can figure it out on the spot. What should the x equals absolute value y function kind of look like? Well, it's not a function, it's a sort of graph, I guess, a relationship. And the answer is, well, you know, let's make a little picture or something. Plugging in various values for y, well, when y is 0, x is going to be 0, but when y is either positive 1 or negative 1, x will be 1. And when y is either positive 2 or negative 2, x will be 2. And so what we get is something that looks like this. Okay, no surprise, it's just like the normal graph of absolute value that we're used to, but now sort of sideways. Okay, and what should I then say? Supposing I have figured that out, what should I then say about the curve x equals absolute value y minus 3? Well, that's going to perform some kind of transformation on this sideways absolute value sign. It's going to move it, sideways absolute value curve, it's going to move it up 3. Okay, in other words, 1, 2, 3, 4, 5 or something like that. Maybe I want to even go up until 6. When y is 3, x will be 0. When y is 4, x will be 1. But when y is 2, x will also be 1. When y is 5, x will be 2. But when y is 1, x will also be 2. And yeah, and when y is 6, x will be 3, but when y is 0, x will also be 3. So okay, this picture could be a little bit better, but good enough. How does this curve get traced out? Well, you can just plug in some t equals values, and like maybe say t equals 0. Where am I at t equals 0? Answer 1, 2. So I'm here at t equals 0. At this point, 1, 2. Well, how about when t is 1? Where am I? 2, 3. So I'm here at... Sorry. I did something wrong. Did I do something wrong? When t is 0, I'm at 1, 2. When t is 1, I'm at 0, 3. So I'm here, 0, 3 at t equals 1. Where am I at t equals 2? I'm going to be at 1, 4. So 1, 4 here at t equals 2. And I think I probably am just moving up like this. Where am I at t equals negative 1? Negative 2, 1. Sorry, second try. At t equals negative 1, I'm at 2, 1. 2, 1 at t equals negative 1. Etc., etc. Okay, so this problem really is, I think, just kind of easy. Boom, 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 boom. You could get it in a lot of different ways. That's all there is to it. We're going to go jump like this and then jump like that. Hitting the sort of bottom here at time t equals 1. This is at t equals negative infinity. As my initial calculation tells me, I'm over here. And at t equals infinity, I'm over here. So, okay, great. More. 17. This is actually very similar to a problem that we already did. So maybe I don't need to do this. I kind of don't want to. But, you know, here we are. Let's go. Number 17. Going a little kind of fast now. X equals 1 plus 1 over t. Y equals t minus 1. So suppose I'm like a professional and I don't need to talk this out endlessly. I'm just going to do it kind of fast. What is there to say? Here's something to say. T can't be 0. Hey, here's another thing to say. Since t can't be 0, that means y is never negative 1. So y can't be negative 1. But also, since 1 over t is always non-zero, then that means that x is never going to be 1. Okay, those are my restrictions. What else? Well, I need to investigate what happens as t goes to infinity. But I also need to see what happens as t goes to negative infinity. And I also need to see what happens near other values where t is undefined. And in that case, we're talking about when t is 0. So when t is near 0, x is going to be huge. So we need to investigate what happens as t approaches 0 plus and what happens as t approaches 0 minus. So the full kind of accounting for the behavior of this problem is going to involve us doing these four regions, these four sort of these four analyses of what x and y are doing for different values of t. Okay, let's do it. As t goes to infinity, 1 over a huge positive number is going to be a tiny positive number, and so x is going to be a little bit more than 1. Y is going to go to infinity. But now, if I plug in like negative a million, 1 over negative a million is going to be a tiny negative, so it's going to be a little less than 1, x is. And as y goes to negative infinity, this is going to negative infinity. How about if t is a tiny positive? Well, 1 over a tiny positive is a huge positive. So x is going to infinity. And What about y? Well, if you give me if you add a tiny positive number to -1, then I'm going to be basically -1, but a tiny bit more than -1. And let's see, how is this looking? Pretty good, I guess. Now, how about as t approaches 0 minus? Well, now 1 over a tiny negative is going to be a huge negative. And if I add a tiny negative number to -1, I'm going to be basically -1, but a little bit less, which is to say more negative. Okay, that I think is really the important part of this problem. And if you get all that right, you sort of can't go wrong. Let's eliminate the parameter. Well, because I have a y equals bias, I'll just do it the normal way. So take x equals 1 plus 1 over t, and solve for t. I get x minus 1 equals 1 over t. So therefore, t is 1 over x minus 1. And if that's true, then y is just going to be that minus 1. So this is 1 over x minus 1 minus 1. And that's pretty comforting because that is just a simple, straightforward curve that I already know and love. It's going to be, yeah, cha. And what's it going to do? It's going to be 1 over x curve, except moved 1 to the right, and also down 1. So moved 1 to the right, and also down 1, and sort of the two facts that I saw at the very beginning have been confirmed, that x can't be 1 and y can't be -1. What does this curve itself look like? Well, it's a normal 1 over x curve, so to speak. So if I plug in like 2, I get 0. Cha. And it's going to look kind of like that. And I guess if I plug in 0, I get -2. So it's going to kind of look like that. Alright, so something like this. Great. Now, what? Let me just add in some t equals values and do some annotations. Well, okay, how about where am I when t equals 1? When t equals 1, I will be at that point 2, 0. So that means this point, this is the point t equals 1 at 2, 0. What's another good number I could plug in? I don't know, t equals -1, where am I? 0, -2, so I'm here at t equals -1, 0, -2. I could probably do more, but I kind of don't want to because I got this under control. Where am I? Well, according to my charts, which I did pretty carefully, at time -infinity, I'm going to be at 1 minus, -infinity. So that means a little bit less than 1. A little bit less than 1, -infinity. So that's down here. So I sort of start at time t equals -infinity down here. And then what am I doing? Over time, I'm moving along this curve. Let's skip ahead to time -1. And now let's skip ahead to time 0 minus. Where am I at time 0 minus? I'm at -infinity, a little bit less than -1. And so what happens out there at -infinity, a little bit less than 1? Answer, instant teleportation at time t equals 0 minus to at time t equals 0 plus infinity, a little bit more than -1. So I stick in a teleporter. This is t equals 0 plus, and then it takes us 1 second to do all this stuff back to the x-axis, and then kind of like beyond, right? I mean, you could plug in other numbers. You could plug in t equals 2, for example. You get 1.5, 1. So great. Okay. And eventually, as t approaches infinity, we end up at 1 plus, infinity. So that means we're here at time t equals infinity. So we start down here, whoop, whoosh, teleporter, whoop. Okay, good. That was 15 and 16. Like I said, we did 17 in class. That was 15 and 17. We did 16 in class. So I think there are precisely 4 problems left to do from this original unpack it, let's just do them all right now. Let's see, do I want to maybe take a picture of this? Maybe I do. Sorry, do I want to take a picture? I guess it's a good idea to do so. So, sorry, hang on 1 second. I'll just take a picture of this board. Something that seems like a good thing to do for posterity. Yeah. Alright, erasing, and then we're going to do the last 4 problems from page 6. Okay. Good. So, 18 and 19 are in fact very similar. And, okay, well, let's just do it. X equals 5 cosine squared t. Y equals 3 sine t. Okay. And what's 19? X equals 3 cosine t. Y equals 4 sine squared t. Okay, in both cases we have some functions which are periodic. In this case, y has period 2 pi, x has period pi. In this case, y has period pi and x has period 2 pi. So both of these are going to repeat every 2 pi. What is there to say about them? Well, I can take the sine and cosine of anything, so there are no restrictions on t, but there are some restrictions on x and y. And, okay, maybe it's not necessary to go through this whole thing every time. I don't know. Maybe it is. What can I say about cosine? Well, cosine is always between -1 and 1. So what can I say about cosine squared? Well, the square of something which is between -1 and 1 is guaranteed to be between 0 and 1. Therefore, 5 cosine squared is guaranteed to be between 0 and 5, and therefore x is between 0 and 5. Fact. What can I say about sine? You can probably just do this in your head, I don't know. Sine is between -1 and 1, so 3 sine will be between -3 and 3. And so y is between -3 and 3. So, what does that tell me? It tells me that my curve is bounded within some sort of box. And now I'm just going to get ready to make this picture right now. And the picture is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Cha, cha, cha. And so there's some kind of rectangle here. And my entire function, or I shouldn't call it a function, my entire curve is going to live within this rectangle and repeat itself every 2 pi. Okay, well, there's only one thing left to do because there's no end behavior to talk about, and that is to eliminate the parameter. And here, because I am experienced, it's just clear to me that the thing to do is to start with 5 cosine squared t, and to replace that cosine squared with 1 minus sine squared. Why? Because I'm looking for, ignoring the 5 and the 3 temporarily, a relationship between sine and cosine squared. And the relationship between sine and cosine squared is that sine squared plus cosine squared is 1. Or rather, that cosine squared can be rewritten as 1 minus sine squared, which means, for our purposes, that I can rewrite sine for what it is. What is sine? It's y over 3. Okay, and pretty much already I am done. And by done I mean I have written the relationship between x and y, the t is gone, I've eliminated the parameter. Cleaning this up a little bit, what do we see? This can be rewritten as 5 times 1 minus y squared over 9. So distributing the 5 through, what I really get is that x is 5 minus 5/9 y squared. Okay, I'll put a box around that because I think that is a good form to have your equation in, and it tells me everything I need to know. What is this? It's an x equals y squared parabola. In other words, it's a sideways parabola. Also, the leading coefficient is negative, which means it's going to be opening left. Also, when y is 0, x is 5. So all of this tells me that when y is 0, x is 5. So we have this sort of dot right here. And I guess I could plug in other numbers even. Like, what about when y is 3? So the corner, when we're at the top of the box. Well, when y is 3, hold on a second. This is the wrong box, of course, because x has to be between 0 and 5. So, okay, well, good thing I caught myself before doing anything really wrong here. In fact, maybe one thing that I could have noted is that x is just positive. This is, of course, more information, but that's even more sort of glaring. Okay, so whatever I was about to say, I think or whatever I was expecting turned out to be wrong because I was kind of being a little careless, but certainly x is positive, and certainly x is between 0 and 5. So, okay, this problem's even easier than I thought. What can I say when y is 3? When y is 3, we just get that x is 0. And so, what is this? It's a sideways parabola, and this is just the whole parabola right here. And I could do more here, but maybe I don't even want to. The potentially other thing that we could do is factor out negative 5/9. Some people like this kind of thing. This gives me y squared minus 9. If I did that right, I did. Why might that be something you wanted? Because it is nice to write your polynomials in factored form. So this maybe is even more sort of clear, or it's another way of looking at this relationship. It's a sideways parabola with leading coefficient negative 5/9. So opening left with y-intercepts 3 and negative 3. Okay, there's only one thing left to do here, and that's label it with some annotations so we can see what's going on. Let's see, where am I at t equals 0? When you plug in t equals 0, you get 5, 3. 5, 3? 5, 0. Yeah. So here we are at 5, 0 at t equals 0. What happens next? Maybe we plug in pi over 2. If we plug in pi over 2, cosine pi over 2 is 0. So we're at 0, 3. So alright, up here at 0, 3 at t equals pi over 2. And then at pi, cosine pi is cosine pi is negative 1, but then it's squared, so we also get 5, 0. So I'm back again here at t equals pi, and at t equals 3 pi over 2, I get 0, negative 3. So here I am at 0, negative 3. At t equals 3 pi over 2, and then sort of back again here at 2 pi. Okay, so what is this thing doing? It's kind of doing this thing where it starts here at 0 and then goes up here. It takes pi over 2 to get there. Then back here. It takes pi over 2 to get back. Then back here. And then back here. So it's kind of just like a jump, 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 jump. And this is maybe one way of showing that. Okay. Oops, forgot to do this. A little bit of a glare. Hopefully that's better. What about the number 19? Okay, it's like exactly the same thing, kind of. I hesitate to even do it. Maybe we'll just kind of do it a little bit fast style, right? So here I noticed that y is to be greater than or equal to 0, but actually I can say even more than this, right? X is 3 cosine, so x is just like a cosine curve with amplitude 3. So what can I say about x? It's guaranteed to be between negative 3 and 3. What can I say about y? Sine squared is always between 0 and 1, so y has to be between 0 and 4. And now I'll just go straight to eliminating the parameter. Well, here I think if you followed what we just did, this is just kind of like another practice or something. What can I say about sine squared? The best way to rewrite sine squared is 1 minus cosine squared. Why? Because I know that x is basically cosine. In particular, x over 3 is cosine. So now that's what I do right now. I stick in for cosine x over 3. Cha, 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 cha. And that there we sort of did it, right? We eliminated the parameter. And what do we get? We get that y is 4 minus 4/9 x squared. And you could leave it like that. I'll put a box around this. Or you could take the additional step of factoring out this negative 4/9, leaving us with x squared minus 9. Yeah, no, yeah. Negative 4/9 times negative 9 is plus 4, which is really negative 4/9 x minus 3 x plus 3. And so you have two different sort of ways of thinking about what's going on here. On the one hand, this is just a parabola. What kind of parabola? Upside down parabola. When x is 0, y is 4. So 1, 2, 3, 4. Boom, boom. But also, it's a parabola which is upside down and has roots at 3 and negative 3. So this is kind of just the y equals version of the previous problem. And as we said up top, x has to be between negative 3 and 3. Y has to be between 0 and 4. It's a terrible looking parabola right there, but I think you get the idea. It's a truncated parabola which meets these requirements. Y is always 0, and we're probably just going to end up going kind of like back and forth and back and forth. Let's do it. Where am I at t equals 0? I will be at 3, 0. So boom. Here at 3, 0 at t equals 0. Where am I at pi over 2? Cosine pi over 2 is 0, so that puts me at 0, 4. So at 0, 4 up here at the vertex, that's t equals pi over 2. I guess that's kind of a little bit different. I don't know. T equals pi, where will I be? Negative 3, 0. Great. T equals pi. I'll be there at negative 3, 0. And now, how about 3 pi over 2? Cosine 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1, but it gets squared, so we're back here at 0, 4. So it's t equals 3 pi over 2. We're also back here, and then we'll be back here at 2 pi. So what is this doing? It's starting here, and it's going jump, 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 and then it's just going to keep doing that forever. So we can annotate that like so. Cha 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 cha. Okay. Great. 2 more to go. Let me just turn this. Maybe that's better. 19 and 20, and then that will, I think, be the end of this video. Okay, so 19. 19. This is a little kind of twist or something like that. Here we have x equals 8 cosine squared, y equals 6 sine squared. Okay, well, once again, doing this kind of quickly because it's a little bit repetitive. I just know that sine and cosine always stay between 0 and 1. So they're squared between negative 1 and 1, rather. So their squares are always going to be between 0 and 1. So I say that x here is going to be between 0 and 8, and that y is going to be between 0 and 6. Also, they're both positive. Okay, this is kind of redundant because I just said that right here, but it's also just jumping out at me, worth mentioning. There's no end behavior to talk about, so I guess I'm just going to eliminate the parameter and go right for it. Well, what parameter is there to eliminate? Here's what I know. I know that sine squared t plus cosine squared t is 1. And so, when I go to eliminate the parameter, what do I find? Well, sine squared is in fact just y over 6. And cosine squared is in fact just x over 8. And so what is this? It's just a line. So the relationship between x and y in this case is just linear. And this is one of these somewhat obscure but actually kind of nice equations of lines that they teach you in Algebra 1. But maybe they don't really care if you learn it or not. And maybe neither do I, but alright, what's nice about this is the so-called intercept-intercept form. And, well, if you plug in, let's see, how do they do this? If you plug in 0 for y, then it's clear that x has to be 8. So when y, in other words, when y is 0, 4, 5, 6, 7, 8, x is 8. So that's my point, 8, comma 0. And when x is 0, then you get y over 6 equals 1. Well, that's only true when y is 6. So when x is 0, y is 6. So this intercept-intercept form is a nice way of leaving your equation, your linear equation, because it's sort of it's from inspection you can see immediately, you know, what the intercepts are. And so yeah, believe it or not, this whole path traced out by this pair of equations is actually just this line. And because x stays between 0 and 8 and y stays between 0 and 6 and x and y are both positive, we stay in the first quadrant. And yeah, these functions are, these curves are sort of, these equations are periodic and bounded, and so actually this is the whole thing right here. How can this happen? Well, just plug in some points to sort of understand it. If you plug in t equals 0, then cosine 0 is 1, so you just get 8 comma 0. So okay, I'm here at t equals 0. I wonder where I am at t equals pi over 2. Cosine pi over 2 is 0, sine pi over 2 is 1, so I'm up here at t equals pi over 2. Okay, that's nice. What's next? Well, where am I at pi? Okay, cosine pi is -1, so I'm back again. So this is pi, and sine pi is 0. I'm back here at 3 pi over 2, and back here at 2 pi. And so this whole thing is just going like zoop, 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 zoop. That's very exciting to me. So let me put a little bump, 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 bump around this, and let's just add in some arrows to indicate that it's just kind of going back and forth along that line. Okay, last problem, number 21. This one's quite hard, I think, and, well, is it hard? I don't know. X equals 8 cosine cubed, y equals 8 sine cubed. Okay, so here's a pair of parametric equations. What can I say about this? Well, first of all, for all the same reasons that we've been discussing, sine will stay between -1 and 1, so sine cubed, if you cube something that's between -1 and 1, it will also be between -1 and 1. So hopefully I can just skip this, just keeping the video kind of short-ish, and hopefully everyone agrees. Yeah, this thing needs to be, this thing lives between -8 and 8. And so maybe already I want to make my graph down here, because even if I don't know anything, I can still sort of plot these 4 points, and they are, you know, 8, 0, 0, comma 8, -8, 0, and 0, comma -8. How do I know? I guess I'm getting ahead of myself a little bit. How do I know we hit those points? Yeah, I mean, you just plug in some values, right? Plug in t equals 0. I mean, the idea is that the cube of 1 and 0 and -1 is just also 1 and 0 and -1. What I mean by that is this curve is going to give the same values if those were instead just sines and cosines instead of sines cubes and cosine cubes. In other words, plug in t equals 0. What do you get? Cosine 0 is 1. But the cube of 1 is also just 1. So you get 8. And the sine of 0 is 0. So, so the cube of sine is also 0. And so you're going to get 8 comma 0. So indeed, we're here at t equals 0. Then how about pi over 2? Well, cosine pi over 2 is 0. So the cube of that is still 0, etc., etc. Sine of pi over 2 is 1. So the cube of 1 is 1. And so we end up here at t equals pi over 2. Okay, and I'm going to be here at t equals pi, and here at t equals 3 pi over 2. So what we have is some kind of, I don't want to say circle, but it's kind of a circle in the sense that, you know, it's bounded and it's sort of hitting the same points that the circle will hit. But what does it actually look like? Well, to figure out what this actually looks like, let me, as I did before on a previous problem that was very similar, let me just blow off the 8 for a minute, because the 8 is kind of just a distraction, right? X is cosine cubed t, y is sine, this is like the sort of the real problem. If I can figure out what's going on here, then my problem is just that dilated by a factor of 8. Okay. What can I say about this curve? Well, I think, as before, I think what I really need to do is to learn something about y equals sine cubed. This was actually a problem on your graphing packet from 2 weeks ago. So, all right, without further ado, let's just ask ourselves, like, okay, y equals sine cubed t. What's up with that? And all right, well, we'll go through a similar conversation as one we had earlier when we were doing cube root sine. So here's pi over 2, pi, 3 pi over 2, 2 pi. So let me just notate those. Okay, so maybe first we should look at regular sine. For that, I will use red. What does regular sine look like? It, you know, it does its thing that regular sine does. It's 0, then at pi over 2 it's 1, then at pi it's back down to 0, 3 pi over 2 back down to -1, and then zoom zoom. Okay, so we got a little bit of this type action, and maybe even we add in an extra little bit. Okay, great. So that's just like sine t. But I want to talk about sine cubed t. What is the relationship between sine cubed t and sine t? Whenever sine is 1, sine cubed t will also be 1. Whenever sine is 0, sine cubed t will also be 0, because 0 cubed is just 0. And if you cube -1, you get -1. So I'm just performing a graphical cubing is what I'm really doing right now. And now I have to ask sort of the deep question, which is, what happens to sine if you cube it? Well, what happens to a number in general when you cube it? Well, in general, when you cube a number, you probably think it gets bigger, right? 2 cubed is 8. 3 cubed is 27. That's true, but not for numbers between 0 and 1. When you cube a number between 0 and 1, like 1/2 say, then you get 1/8. And so cubing a number is a process which makes numbers between 0 and 1 smaller. And now that I realize that, I see that sine cubed is going to be, relative to sine, it's going to always be smaller. It will have y coordinates which are in general less than the corresponding y coordinates on the sine curve. What you're going to get is a kind of emaciated curve, which is just smaller in every respect. And what can I say at the origin? Well, to repeat this kind of conversation from the other video, you should recall that you know, when t is approximately 0, sine t is approximately t. So what should I say about sine cubed t? Well, if sine looks very, very much like t for tiny values of t, then sine cubed is going to look a lot like t cubed. And so we should expect this purple sine cubed function to, when we zoom in at the origin, be locally cubic. That's what we expect. Okay. Great. Keeping that in mind, what bearing does that have on my curve? Well, what I should expect then, if sine and cosine together parameterize the circle, then what should I say about sine cubed and cosine cubed? Well, they are going to be circle-like, but at every single value of t, the sine cubed and cosine cubed are going to be smaller than the corresponding sine and cosine curve, which make a circle. So what is this going to be? This is going to be a circle that's kind of like fish face, like sucked in a little bit, right? The x and y coordinates are going to be both smaller at every point than sine and cosine, which make a circle. And so what you get is a kind of sucked in circle. And the actual answer here is you get this thing that looks kind of like a star. And this has name. This is called the asteroid. And okay, see me later for some sort of deep conversations about this shape and why it is so awesome. And actually we'll see this again in calculus, I think. And there's a geometric definition that's possible about the asteroid, but kind of there it is. It's going to go sort of in like this. And I think in this case you can get some decent points if you just plot like pi over 4, right? When you plug in pi over 4, what do you get? Well, cosine pi over 4 is root 2 over 2, and when you square root 2 over 2, you get 2 root 2 over 8. And sine is the same thing. So actually, you do get, you could get another nice point here if you really wanted to be awesome. This point is 2. Did I do that right? Yeah, 2 root 2 comma 2 root 2, and that happens at t equals pi over 4. And if you did 3 more of those, you could make this graph a little bit more accurate, you know, kind of if you wanted. Okay, good. That completes Parametric Equations Packet 1.